We're going to spend all of lecture 5 really working in that step 1 script that we had opened and discussed at the end of the last lecture. So if you're on the course website and you scroll down the syllabus, we've already completed read mapping using Callisto, and we spent a lot of time in the last lecture talking about the output that Callisto produces and how we think about units for describing digital gene expression and how these units relate to really fundamental concepts in transcriptomics like normalization. At the end of that lecture, we opened RStudio, we started our first R project and discussed why it's advantageous to work in the context of an R project. And then we opened the step 1 script and sort of took a step back and used that step 1 script as a way to discuss some general things and ways to think about working in R in general, like how we access packages and download and load them into our environment, how we structure a script using code chunks, and more, and how we think about comments and that sort of thing. We're going to review that briefly at the start of today, but I'll move sort of quickly so that we can get to the new stuff. So today we'll open that RStudio project. We'll pick up right where we left off. We'll open that step 1 script and we'll start executing lines of code. So let's take a look at the goals for today. I just want to mention first, really no lecture slides for today. We'll really just spend the entire time working in the step 1 script. And the next lecture will be essentially the same, very little or no slides, mostly working in the step 2 script. Your homework is the second homework assignment now for the course. It's the introduction to the tidyverse, which relates to topics we'll just barely touch on today and that we'll deal more with in the next lecture. But that homework's due before the start of class on Friday. So, learning objectives for today. We're going to, as I said, move quickly reviewing the basic elements of a script and how to access R packages and help documentation. We're also then going to spend a little bit of time reading our study design file from our hard drive. This is the study design file you accessed from the course website. We're going to load that into our R environment, and this gives us a chance to talk about how we get any data from our computer or even from a website into the R environment. We'll then do something that's really essential and unfortunately sometimes represents a frustrating hurdle in RNA-seq data analysis, which is accessing annotation information for transcripts. And we'll do that using bioconductor packages. We'll talk more about what I mean by annotation when we get to that point. And then we'll conclude that step 1 script today, and we'll be done with it. And we conclude it by actually reading our Callisto transcript abundance, all of those Callisto outputs that are sitting in folders on our hard drive, reading that data into the R environment. So the step 1 script is available here, and this is a good point to just remind you that if for any reason you've had trouble aligning the raw data and generating those Callisto outputs, this is the time to go and just do option 2. Just download the Callisto output folders, and that allows you to bypass the alignments altogether. You can always go back and sort this out and figure out how to do these alignments yourself. But if you want to sort of keep pace today and follow along, it'll be important that you have Callisto outputs available. So just download them here. It'll be a single zipped file, unzip it, and you'll have all the folders that I have. You're also still going to want this study design file, as I said. That's the study design file. We'll actually sort of begin the script by reading into our R environment. Okay, so I think we're ready to get started. So I'm going to actually navigate to my file system here. And I just want to remind everybody, I'm working in a folder that has all my Callisto outputs. So they're directly there in my work environment. That's the same folder I set up my R project in. We want to make sure that these Callisto outputs are in the same folder as our R project. If they aren't, then that creates problems when we go and look for them because this R project only looks in this folder unless you tell it otherwise. This is also a good point to just remind you that all those FASTQ files that we were working with before that take up a lot of hard drive space and that index that we created, if you'd like, you can delete those to free up hard drive space. You can also keep them. It's up to you. But I know some of you had trouble even storing all this data. So at this point, if you've got the Callisto outputs, you can go ahead and delete those files. All right, so current working folder has your Callisto outputs, the R project, and then also importantly has your step 1 script and the study design file that we'll use today. Those are the essential elements you need for getting through today's script. So to start today, we're going to actually just double click that R project file, let it open RStudio for us and already be looking at the right working directory and pick right up with that step 1 script open and everything as we left off. Great. So here we are, and I'll just quickly review a few key things from the last lecture. If you go to Edit, Folding, Collapse All, you will see a signature of what I do with all the scripts I'll use for this course, which is organize them into these sort of digestible little code chunks. And this provides a few advantages. We can talk about each chunk independently. We can execute these codes of chunk and know that we've accomplished something. It also gives you this high-level view of sort of what we're accomplishing with each step script. As I mentioned in the last lecture, I will always start these the step scripts with an introduction. I'll always then have a chunk dedicated to just loading packages so that it's immediately apparent to you what software we need to do what we're going to do in that script. And then I'll have sort of the chunks that relate to what we're trying to do in that script. But then I'll always end the script with sort of the minimal essential code you would need to reproduce everything, even if you strip away all the teaching stuff that I'm doing. And these will become really important at the end of the course. All right, one thing that I neglected to mention in the last lecture is there's a sort of added bonus in structuring your scripts this way using code chunks. And that's that RStudio recognizes this kind of structure and uses it to create or format a table of contents. And that table of contents is available to you in two places. One is just below the script editor right here. So that pop-up window, you can see the names of these lines are exactly the same as the names of my code chunks. And it's also available here as a side window. Why is that useful? Because step 1 happens to be a really small script, but as we string these scripts together and as you work more in R and you get longer and longer sort of workflows, it can be really challenging to figure out where you need to find something in a script. So having code chunks really helps with that, but having a table of contents then lets you jump between these code chunks really quickly. So if I were to say edit, folding, expand all, this is a total of 100 plus lines of code and comments. I could jump down to that last code chunk really quickly. Just clicking on it in the table of contents immediately drops my cursor right at the start of that code chunk. All right, I can hop back up to the top here just by clicking on the first code chunk. As a reminder, making anything into a chunk is just a matter of adding 4 or more dashes at the end of a comment line. Comments, of course, prepended with these pound signs. Doing that gives you this foldable arrow that lets you open and fold the code chunk. That's it. So I'm going to hide this window, but just know those table of contents are always available to you in those two places. Okay, we don't need to review the introduction anymore. It's time to just quickly review loading packages. One thing you may notice that I haven't shown you here is that if you're opening an R script for the first time, RStudio kind of parses that R script and looks for this library function. When it sees that, it looks at package names, and if it doesn't see those package names anywhere in your library, sometimes RStudio will suggest that you download them as soon as the script opens. It'll have a little pop-up window that says, we see you need these packages and you don't have them in your library. Would you like to download them? That's a super easy way to just get what you need to run a script. And I would encourage you to just say yes and install those R packages. I'm not getting those kinds of pop-up messages because I have all these R packages installed already. So just as a sort of side note. Okay, so as a quick refresher, to install R packages, you just hit install, and you could type what you want to install, but you're only looking at the Comprehensive R Archive Network, or CRAN, as the only repository. So I mentioned to you that one thing you'll want to do is hit set repositories, or start typing set repositories, allow RStudio to autocomplete, and then hit enter. And it'll allow you to choose multiple default repositories to be looking at, and I encourage you to just choose all of them and hit enter. And then when you choose install, you now see that you're looking at all these repositories, and you can just start typing the names of packages. For example, our HDF5, I can type tidyverse. I can, and these can be comma separated or just space separated. TXI import, and RStudio is doing its autocomplete now. Ensemble DB, ENS DB. This is the human annotation database package. We actually want the most current one. So you can see some packages, well, for annotation packages, we see multiple annotation versions, multiple releases of annotation data for the human genome. I'm going to choose version 86, the most current. Biomart and beeper. All right. Another thing to notice is that no matter what you type, R is keeping the sort of case sensitivity of this, and that's important. R package names are case sensitive. If you were to type in, ENSDB without that capital D, and you try to download or load using that slightly altered package name, it won't work. So that's one nice feature of the autocomplete is it doesn't allow you to do that. I tried typing beeper, if we can try it again, with a capital B, and it uses that. Its search function is not case sensitive, but when you find the actual package name and click it, it corrects it to be appropriately case sensitive. So at this point you would hit install. I'm not going to do that because I've got all these, and it takes a couple minutes, especially for some of these larger database packages like the human Ensemble DB package. So I'm just going to hit cancel and know that I have all these installed. Now, one thing I'll have you add to this script right now, so hopefully you're paying attention here, we're going to load an additional R package that's called data pasta. And data pasta, again, a package I already have loaded, downloaded and installed in my R environment, is just a useful package for allowing you to paste, that's where the pasta comes from, to paste data into R. So it'll take data that's copied to your clipboard on your computer, right? And it'll allow you to quickly get that in. So I'll demonstrate that in a little bit, but so this is great for copy, paste data into the R environment. Okay. All right, that's the quick and fast overview here for loading R packages. Now, we've got those packages in our library, but remember, we haven't actually loaded them until we execute these lines of code. So we're going to do that now, and we're going to watch down here in the console as we do that. I'll start with our HDF5. I'll go on to tidyverse. And there's already been a comment about this on the Slack page that this raised some concerns for people that you get this information or message back from tidyverse when you load it that says, hey, I'm attaching these other packages and I have some conflicts. So let me just briefly explain. Tidyverse is actually not one R package, it's 8 R packages. And so when you run that single line of code, it's actually loading all 8 of these packages. And you could just confirm that if you looked for any of these, like 4cats. You can see that 4cats, which is a tool for dealing with categorical variables, creative name, is checkmarked. So it's loaded. And indeed, it loaded 4cats, right? So just be aware, tidyverse, as the name suggests, a universe or an ecosystem of R packages. The other thing it said is that there are some conflicts, and you'll see these conflicts deal with or relate to functions from one of the packages in the tidyverse called dplyr, and in 2 functions in particular. Dplyr has a function called filter, and dplyr, the package, also has a function called lag. Both of these function names are pretty generic, right? I mean, filter, you could imagine a lot of other R packages and authors of a lot of other R packages coming up with another function in their particular package that also has the name filter or lag. And indeed, that creates a problem for R, because if you've loaded dplyr and maybe some other R package and both have a function called filter, when you go and call on filter as a function in your R script, the RStudio and R won't know what package you mean. What should they take filter from dplyr, or should they take filter from the stats package? And so what tidyverse is saying here, and what they're alerting you to, is that they have now set their package from dplyr, their function filter and lag, to be the default and to mask potential conflicts that could arise if you had the stats package loaded. All right. Now, we'll discuss this later, but this double colon helps us resolve all of these things anytime there's ambiguity in package names, in function names. Okay, so that was loading tidyverse. Now let's load tximport. That's the package we'll use for actually getting all of our Callisto data into R. We're going to load EnsembleDB, and we're going to load the human database or organism package here. And this is R is still thinking. I can see because it's got its little stop sign there. So it's got to load a lot of stuff for EnsembleDB to work. Now I load the organism specific database package. That's loaded. I'm going to load Biomart for a way to get other annotation information when we're not dealing with human and mouse. Just a little package called Beeper that we'll play around with. And then, of course, Data Pasta, which I already mentioned. All right, so that really gives us all the tools that we need for today. They're not only downloaded in our library, but we've pulled those books off the shelf, if you will, and they are open and ready to be used in this session. Okay, so we now are done with that next code chunk, and we're really here, which is the third code chunk, just reading in our study design. As I mentioned, we're going to read in a single file. But this is a good opportunity to just talk about getting data into R. So we're going to read our data into R using one of the tidyverse packages, in particular a package called reader. And reader has a function called read TSV. We're going to talk more about these read functions in just a minute, but as a very general kind of overview here, this is very typical of the kinds of lines of code we'll be running. Oftentimes they involve a function. They always involve a function. We're doing something. I think of functions as the verbs of our R sentences. And then as you've already seen, we have parentheses after that function, and we have what are called arguments that can augment or dictate how that function is going to operate. So that's what's happening here on the right side of this sort of arrow. But we now have the first time we've seen an assignment operator. You've seen this in your homework. I use the less than sign and a dash, but an equal sign is equivalent, but can cause some problems or confusion later, because equals is also useful in other contexts in R where it means something different. So to avoid any confusion, I just suggest you go with this assignment operator. Now, what is an assignment operator? Well, it takes the result of running this function with these arguments, and it puts the result into an object that you've called targets. Now, it's important you understand name here doesn't matter. We could just call this T. We could call it, my thing. It doesn't matter. I'm calling it targets, and I'll call it targets throughout the course, but that's just the label I've chosen. You can call things whatever you want. It doesn't change the nature of what's created here. It just changes the way you'll call on it down the road. Okay, so when I run this line of code, read TSV is going to go and do its thing, and it's got a single argument, which is the name of a file that sits in my working directory, and that's important because if it doesn't, it's going to throw an error and say, hey, I don't see this file. But that's the only argument I've specified. And there's a good chance with many R functions, you're not going to know what arguments there are and how to think about it. Now, if I just double click read TSV and I leave my cursor over it, I don't even need to double click actually, I just need to just put my cursor on read TSV. You immediately can see read TSV and then all of the arguments that are available. There are arguments that are default and have default settings, like call names is set to true, call types is set to null, and so on. In fact, all of these arguments have defaults except the first one, which is you can't use this function unless you tell it what it should read. It needs a file name. So if we were to put nothing in this set of parentheses, it would not be happy. It would throw an error. All right. So we're going to run this line of code, and we're going to produce an object here in just a minute. I just want to highlight that there's other ways to get information about functions. So before I run this code, it's just a brief aside. If I were to type question mark and then the name of the function, that is a way, universal way in R to get help. And because I have this handy help tab over here, anytime I do this, the documentation for this function will pop up over here in the help tab. So I'm going to run question mark TSV, and it automatically switches over to the help tab, and I can see that read TSV is from the reader package, and it's actually just a variation on another function called read delim. In fact, read delim is really the function name. Read TSV is just read delim with some different arguments specified by default. So the description of the function is here, and I can see the usage, read delim, and then read CSV, read CSV2, read TSV. These are, again, these last three are all just variations on read delim. If I want to know more information about what these arguments are and what needs to be specified and how to use them, I have a detailed list of the arguments below. So this is even more informative than just, placing my cursor over the actual function, right? I get a lot more information here in the lower right than I do just by mousing over. So that's why I wanted you to see this. And then lastly, I get examples. So I get reproducible examples of how this code, how this function can be used. Now, one thing a lot of people don't realize is that in this examples section, and actually anywhere in help documentation, you can highlight a bit of code and you can actually run it just like you would run code up here. Now, I have it highlighted. I'm going to do my code execution shortcut, which is, Apple return. And I can see that it ran that code from the help documentation right here in the console. Read CSV, reader example, empty cars CSV. Where the heck is this empty cars? Well, it turns out there's a fair amount of data actually already available to you in R that's been loaded. So that was the other thing I want to show you, is that if you were to type data, open and close parentheses, you're going to, and run that line of code, you're going to see a pop-up tab here that has all of the data sets already loaded in R. And there's several dozen of these data sets. Empty cars is right here, and it's a common sort of toy data set that you see a lot of demonstrations with in R. Another one is the iris data set about flower petals. So any of these could be called at any time. You could get data on topographic data on volcanoes, diameter, height, and volume for black cherry trees. These are just currently available to you. And so when I ran this example piece of code, that's what was happening. It could already get this data because that data is available. Okay, so question mark function name will get you information about the function. Help will do the same thing. You can see the options here, but I just tend to use the function name. If for some reason you're not getting anything from question mark, 2 question marks is essentially will instruct R to search all help documentation for this phrase. And so running that will open up a different sort of display here in just a minute. Still thinking. And it would basically say, hey, I found that sort of search query in the following help documentation pages, and you could click on them. All right. So I know that's an aside, but it's an important aside because it's essentially how we find help for any function and how we find or use data sets that are already available to us. All right. So I said we were going to actually run this function read TSV, read in our study design file into this object called targets. So I'm going to place my cursor there, and as I've been doing already, I'm going to hit Apple return, but remember I could also just hit run, and I'll do that this time just to demonstrate. Okay, now, this is the first time you've created an R object. You have an object called targets, and that object now appears here as data in your global environment. I can see that targets is 10 observations of 3 variables. From your homework, you might recognize that this is a common nomenclature for referring to something called a data frame, where it's a mix of text and numeric data. I also see that I got some information that came out in the console when I did this, and this is common with many functions, that they'll give you warnings or just extra information. In this case, it says, hey, I saw 3 columns, sample, SRA accession, and group, and I read them all in as characters, okay, as essentially columns that are character vectors. If I ever want to see what targets looks like, there's a couple ways I can do that. One is I can highlight the word targets and hit run, and that'll display it in the console. It executes that object and will display that it's a tibble, which is a table of data that's created by read TSV. It's created by the reader package. And I can see exactly what we just discussed, 3 columns, and the information for the 10 samples. So these are the 10 samples that we're dealing with in this data set. The other way we can do this is we can click on it over here. And in that case, it opens in this handy data browser that actually has a lot of Excel-like features. For example, I can filter on anything here. I can sort by ascending or descending order. There's a bunch of useful sort of point-and-click aspects to this data browser, and I can also search if I'm looking for, a particular sample, HSO2. Now, in this case, we're opening a really small file, but this data browser does a great job searching even really large files. All right, I'm going to close that. In no way does closing that or clearing out this console change the fact that I have an object in my R environment that's not going away. And that's a good thing. To get rid of that, I'd actually have to sweep this clean, which would really remove everything in my global environment. But this is great because it means when I save this R project and I open it back up, I've got all this stuff. I don't have to run that line of code again. Okay, and that's really important. I do not have to run this line of code again. I've already created that object. It's in my R environment. This is kind of a difficult concept sometimes for people to get used to because you're used to things that you create being physical objects you can see in your working directory, and that's just not the case, right? That targets file or object is not a file written to our hard drive. It doesn't exist anywhere in that directory. It's part of your R project. Okay, so we've read that object in. I mentioned you can click on it, you can execute the line. You can also, and you may have noticed this, when you click on this, it actually ran a line of code, view with a capital V, that's important, view targets. So that's again the combination of point and click and command line that RStudio offers. Okay, so we've read in that object. That object is, as I said, a description of each of our samples. Not a lot going on here. We just have a sample name, an SRA accession, and then whether that sample came from a healthy volunteer or a patient with the cutaneous leishmaniasis disease. Your study design, if you're doing this, should include as much information as you know about your samples. All right, and I can't emphasize this enough. If you collected information about sex, age, cage effect or cage assignment, if it's a mouse experiment, whatever experimental variables you recorded, those should be stored in a simple text file like I've done here, because then if you read that into your R environment, those variables are available to you to interrogate and ask whether they impact gene expression, ask whether they contribute to an outlier, allow you to filter your samples. So I can't emphasize this enough. Make sure that anything you know about your samples in your experiment is recorded here. All right, now that we have this object created, we're ready to actually start the process of building up to reading all of our Callisto data in. And the first part of that is to run a function called filePath. As the name suggests, filePath will take any text you give it and create file paths. Now, I have some text I want to give it, which is I want a file path to look at this targets object. So I've said targets and dollar. Now, target dollar does something interesting here. I'm just going to delete it and start typing. Anytime you have a data frame and you name that data frame and then type the dollar sign, it's shorthand for indicating you want to tap into a column from that data frame. In this case, because I'm using RStudio, it just pops up with a selection menu and I can just choose. So that's super convenient, right? It gives you an easy way to access any column in a data frame, and it even has this sort of character to indicate what kind of data is in those columns. In this case, they're all sort of characters, so character vectors, so they have the same sort of icon, but it'll distinguish between numeric and factors and characters. I'm going to go back to choosing sample. So targets dollar sample means I'll just get this column. And I then want the phrase, and I put this in quotes because I want it to be taken literally, I want abundance.tsv. Now, I've taken a column and tried to combine it with a literal piece of text. What will happen here is that it will iterate over this. So file path as a function will take each of these and append abundance.tsv. And it won't just stick it to it with no spaces or with a period. Because it's a file path function, it knows that the way it should connect things is with a slash, a forward slash. So I'm going to go ahead and run this so we can create our second object, which I've called path. And then we'll take a look at what this looks like. All right, now I've got a new object, path, over here. And path now falls under values. It's not data, it's a value. I'm going to take a look at what that looks like by highlighting path and hitting enter. And you can see that exactly as we would want, it iterated over the column in that data frame and took each element of that character vector and appended abundance.tsv. So if we look at our Finder window here, or my file browser, I can see that what I effectively did was set the stage for being able to access each of these folders with almost no work at all, one simple line of code. I could go into HSO1, my first healthy subject sample, and I will be able to get that abundance.tsv file. So that's super useful because no matter how many samples you have, the same line of code would accurately, without any errors, generate the appropriate file paths. If you try to do this manually, it could take a long time and there would be a chance that you would introduce errors. All right, so if I have a lot of file paths, I'd like to know if I got them right. And so that brings us to our third function, right? We did read TSV, we did file path, file exists. Now, I should mention file path and file exists aren't part of the reader package or the tidyverse or anything else. These are just part of the base R environment, right? These have nothing to do with bioinformatics. They're part of what you get when you have R installed. So I'm going to run file exists on my file path. Okay, so my path object, I'm now running another function on the object I created above. But this is the first time you've seen this, which is a sort of nested function. So I'm running this, but the result immediately gets evaluated by another function called all. So when we have situations like this, I'll start in the middle, sort of, and work my way out. So I'm going to highlight just file exists path, and I'm going to run that, and we're going to see what happens in the console. So the first thing that you can see, and again, this should sort of resonate with what you did in your homework this past week, is that file exists creates a logical vector where it evaluates each of those file paths separately and asks, when I go down that path, do I see that file there? Since it's a logical vector, the answer it returns is true or false for each of those file paths. Now, visually, I can just parse this and see that, okay, all my file paths are right. But for larger data sets, it's nice if you can get a single readout for whether all your file paths are correct. So I can pass this logical vector to the function all. All takes logical vectors as, as its argument, and it will evaluate, are they all true? Now remember, when you're evaluating logical vectors, the default is true. So in other words, all is defaulting to asking, are they all true? If the answer is yes, it will return true. If even one of these file paths is incorrect, then all will say false. In other words, not all of them are true. So let's just run this whole entire line now and see if that's the case. And indeed, each of these file paths returns a file, true, 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 true for all 10. So all says true. All is just one function that will take logical vectors as their argument. You can imagine variations on this theme very easily, like any. In other words, are any of these are any of the logicals in that vector true? So not all, but any. And of course, the answer will also be true. And then the function which will take all of those and say which of those are true. And it'll return a vector of numbers. And in this case, I see 1 through 10 listed. Everything I just described to you is down here as well, just so that you can read it and really consider it, because I know that some of this can be a little foreign if you're doing it for the first time. Okay, so we've read in our data. We used the first column, read in our study design file, used the first column of that study design to create file paths really quickly, and validated that all those files exist at those paths. Great. Now we're ready to start getting annotation information. And the reason we want to go ahead and do that now is because we need that annotation information when we actually read our data into R, read our Callisto data into R. So that's where we are now. I'm going to leave off on this for right now, and we'll pick up on annotations in the second part of the lecture.